Okay, so there are some limitations to microbial fuel cells. However, I have Jason Owens here, who is the lead electrical engineer for a startup company called Resonance Group. And so he knows a lot about electronics, and especially batteries. And essentially, the microbial fuel cell is a battery. But from this paper here, published in 2011, it's called Issues of Scale in Microbial Fuel Cells and Bioelectrochemical Systems by these guys from the UK. There's issues with making them big, and since we want to make them the size of a fuel tanker, that's gonna be an issue. So let's just read this real quick. We're not gonna understand a lot of it, but he will, and he'll explain. So, bioelectrochemical cells research has focused mainly on laboratory scale devices to date. In 2008, a study showed they could achieve greater than 2 kilowatts per meter squared. That's a lot. Specific to reactor volume, which was less than 0.5 milliliters. So basically they saw this power concentration in a test of 0.5 milliliters. So that's not a lot. That's like nothing. However, there appears to be a swing in emphasis towards applications. Extrapolating laboratory scale performances to an industrial scale has not always considered the difficulties which need to be addressed to achieve scale up. Let's see, a study, D1, let's see, there's a reference there, considered the frequently asserted assumption that increased electrode area, size of the electrode, so the electrode is where the bacteria cling on to and then release the electrons that creates the power. Or the differential. It's the same thing that happens in a normal battery, right? Okay, yeah. So it's just the bacteria are using it instead of the chemical difference between the lead and the acid. Blah, blah, blah. They showed that there was not a direct linear relationship between specific power density and anode size, but a logarithmic relationship instead. They suggest there may be serious questions to address in relationship to plausibility of MFC scale-up, MFC meaning microbial fuel cells. MFCs are limited in several senses in their current state of development. A critical issue is the spatial arrangement of the anode and cathode, regardless of the presence or absence of an ion exchange membrane. A tension exists between various overpotentials related to ohmic activation and mass transfer losses and volume availability for bacteria and the substrate. Then there's this figure. It says figure 1 indicates the predominant classifications of overpotential losses expected in MFC, where the cell voltage diminishes as current loading is increased. Yes, my brain just melted. This is the thing. I don't know what that means, but he does. So, Jason, can you explain to us what that means?
Sure. So let's start with some basic things. So, as Jordan rightly put, this is basically a battery. So I'm going to use a battery that everybody probably has some knowledge about, which would be a lead acid battery, or the kind that you'd see in like your car, for example. So if you take a battery, or actually any kind of battery, whether it's a chargeable or non-rechargeable type, you may have noticed that if you have a high drain application, if let's say you're powering a remote control car off of a battery, the batteries die faster than if you take the same size battery and you power, let's say, like a flashlight or a watch off of it. And the reason for that is something called the Pukert effect inside the battery. And what the Pukert effect basically means is that the amount of energy that you can pull out of the battery is not linear with the rate that you pull the energy out of the battery. So, for example, let's say that I have a battery that can hold, let's say, 1 joule of energy, just as an example, okay? If I discharge this battery at a rate of X, let's say that the battery lasts for an hour, okay? Now, intuitively, you would expect that if I discharge the same battery at 2x, that it should last for 30 minutes. Or if I discharge it at 4x, it should last for 15 minutes. But in fact, that's not actually what happens. if I discharge the battery at 2x, it may last only 15 minutes. And if I discharge it at 4x, it may last only 3 minutes. So what happens is the battery actually has what we call an impedance, which is it impedes the flow of electricity through it. And this impedance is not constant. It actually changes. And it, unfortunately, just so happens that as you increase the power draw on the battery, this impedance non-linearly increases, or as they mentioned, logarithmically. So what that basically boils down to is you have to be careful about how you discharge the battery, because if you do it wrong, you actually will kill the battery faster than it should be killed. Now, going back to this paper, they were also talking about this relationship between electrode surface area and power density, I think is what they had said. So this is sort of related to what I was just saying earlier, which is as you increase the size of the battery, you would expect that you'd be able to increase the power density of the battery. Well, that's true, but you also have more of these impedances inside the battery that you have to deal with. And in the case of both an electrochemical battery and this biological battery, these impedances are due to the chemical reactions that are taking place inside the battery while you're pulling power out of it. So they mentioned something about overpotentials. So what that really means is that when you're pulling current out of the battery, the chemical reaction inside the battery produces a voltage inside the battery that tends to reduce the output voltage of the battery. And the more you try to pull current out of it, the more of these overpotentials show up, and basically the net result is your battery looks like it's dead faster when it's really not. So as I was sharing with Jordan, actually one of the technologies we're working on to overcome this problem, specifically for lead acid, is something called pulse technology, which is doing exactly what this technology needs, which is to overcome some of these impedance problems that these batteries are facing. So that's one way to approach the problem. The other thing is you can look at changing the way that you design your electrode. So maybe it doesn't need to be just a big flat plate. What some of the current battery technologies actually do is they use a porous type anode or cathode in the battery, so that way you have more physical surface area to come in contact with your active material, whether that's electrolyte or it's the bacteria or whatever is inside the battery. So there's several different ways to approach it, but for sure it's definitely a big engineering problem. Not insurmountable, and interestingly enough, this is something that the battery industry has been facing for years, so it's not a new idea. Just these researchers may not be familiar with some of the challenges that the battery industry is already dealing with right now. So that's kind of my 2 cents on that paper.
Amazing. So I'm thinking there could be some like biomimicry thing that we do with the anode. Like it could be like a porous, like you were saying, porous type of structure. Like I immediately just thought of like a lung-shaped thing, like very, like a variegated type porous structure that goes into this.
Like mesh.
Yeah, like a mesh thing, and it has a lot of surface area. The bacteria can get in there, and so just thinking that biomimicry make the anode look like something that absorbs a lot. Like we were talking earlier with the proteoid roots that develop that have a lot of surface area to absorb a lot of phosphorus. If we make like an anode that's kind of like that, and then that can absorb a lot of, or that can have a lot of surface area for the bacteria to create electricity and stuff like that. But thoughts, stuff, yes.